So let's talk about this Gram-Schmidt autonormalization process. What does it do? Assuming you've got some basis, or well, we don't need it to be a basis actually. We just work on the fact that it's linearly independent, and if you've got enough vectors, it's going to be a basis. So let's say you've got a linearly independent family which has vectors u1 up to un, and you want to build out of this a new family. Um, a new family, let's call that B prime, which will contain vectors E1 up to En, such that they span the same space, of course, and that's the idea. And the span of B is the span of B prime. And moreover, these vectors are orthonormal. Okay, orthonormal. Okay, so orthogonal 2 by 2 and have norm 1. Right, so it's actually an induction process. So let's see how that works. What I mean by induction process is that we're going to make E1 out of U1. That's going to be very easy. We're going to build then E2 out of U1 and U2. We're going to make E3 out of the previous one plus U3 and so on. So let's see what it makes. So first, let's put E1 is the normed version of U1. That's going to be a good one. All right. So normed version is that I just have to multiply by 1 over the norm of U1. Okay. And one abuse of notations that I will often use is this one. I will write U1 divided by norm of U1, which is not a very correct one because here we have U1 is whatever you want. It could be a vector in Rn. It could be a function, a polynomial, whatever, divided by this value, okay? So writing a vector divided by a real number is actually an abuse of notation, but actually, never mind. We can use that. Everybody understands what we mean. And then we're going to make E2 such that E2 is orthogonal to E1, so that's our requirement. We want also E2 to have norm of 1. So, okay, sorry, I forgot to write that. E1 is, of course, norm 1. That's what we did that division for. We want now to build E2 that it's going to be orthogonal to E1. And we want that the span of U1 and U2 is actually equal to the span of E1 and E2. Okay, what does that mean? It means that I already know that the span of U1 and E1 are the same. Okay, so actually it means that U2 can be written as a linear combination of E1 and E2. So let's write that. U2 will be written as a value lambda 1 times E1 plus a value lambda 2 times E2. Okay, and I'm going to, so I'm looking for E2. So let's say that, let's give a name to this one. That's going to be E2 prime. The thing is that E2 prime has the same direction as E2 because, well, it's just real value lambda times E2. So E2 prime is collinear to E2, right? So they have the same nice, they will have the same nice direction. So in other words, what I mean is that I'm going to find E2 prime and then I will normalize E2 prime in order to get my orthonormal vectors E1 and E2. Okay, so out of from that previous expression, I get that E2 prime is actually equal to U2 minus lambda 1 E1. Okay, I know U2, I know E1. What I need is the lambda 1. Okay, so, and for this, I'm going to use the facts, well, I'm going to use that requirement that E2 and is orthogonal to E1. So E2 prime also is orthogonal to E1. Okay, so what does that mean? It means that you know it can be translated into this inner product that E2 prime inner product with E1 is equal to 0. So let's make this on the previous line. Let's take this inner product with E1 and that should be equal to 0 because the left hand side is equal to 0. Okay, so we get that 0. when I can write, we get that, sorry, 0 is equal to, so that's the 0 here is equal to, we said u2 minus lambda 1 e1 scalar product with e1. So now let's expand that using linearity. So u2 e1 minus lambda 1 e1 e1. Good thing is that we made lambda 1 to have norm 1. We made e1 to have norm 1. So that's norm of e1 square. It's equal to 1. So what do I get? I get that lambda 1 is equal to the scalar product of u2 with e1. Which is not very surprising now you come to think about that, because what have we written here is that if indeed I get that E1 and E2 make some kind of orthonormal basis of this span, and this span is the same as that one, we get that lambda 1 and lambda 2 would be the components of U2 in that basis. Okay, and you already know that the coordinates in an orthonormal basis are given by this scalar product. Okay, nice. Right, so what's happening? What do I have now? I've got that E2 prime is actually equal to vector E2 minus lambda 1. So I'm working on that. So E2 prime is equal to U2 minus the lambda 1 which I have just found, U2 E1 times E1. So what do we have here indeed? It looks like to make E2 prime, we take U2, okay, our second vector of the first family, and we subtract from it the component of this vector that relates to E1. Okay, I'm taking away all redundant information in order to keep only the orthogonal stuff, okay, only the thing that is new information and that is not in the direction of E1. Okay, it's just like, okay, you had this first vector, E1, and you had this second vector, let's call that u2, and actually if you want to build an orthogonal component out of that, you have to subtract this piece, which would be something like the projection of u2 on e1, and keep only this part. Okay, so that would be your second vector. That's really what we are doing. We're taking our vector u2 and we're subtracting the e1 component of u2 to keep only the part that is really not redundant, that is orthogonal to the first one. Okay, and now that we've got that E2 prime vector, we just make E2 as the norm version of E2 prime. So 1 over E2 prime, E2 prime. Okay, nice, isn't it? Okay, so now I've got B prime 2 that contains E1, E2 that are orthogonal and to each other and have norm 1, that's the cherry on the cake. All right, and so we can go on this way. Let's make a new one. Let's make a new one. Let's find E3. Okay, to be sure you have understood this process. Let's find E3. So we know we want E3 such that the span of U1, U2, U3 is the same as the span of E1, E2, E3. Okay, we already know. I'm going to just underline what we know. We already know E1 and E2, and of course we know these ones. And we want to build the new E3. So we're going to make the same stuff. We're going to say that U3, okay, that's the novelty here. U3 will be a linear combination of E1 plus E2 plus E3, okay? And I'm going to call that E3 prime. And I'm going to say that E3 prime, which has the same direction as E3, will be at the same time, when I can write, Okay, so E3 prime is orthogonal to E2 and to E1, so with the same consequences on the scalar product. Okay, so from this, I've got that E3 prime is actually U3 minus lambda 1 E1 minus lambda 2 E2. You see, it's the same structure as before. We are taking out of our vector U3 the components along the directions E1 and E2 so that we keep only the new information, the non-redundant information out of this vector U3. Okay, so we do the same thing. We say that E3 prime with E1 is equal to 0 because they have to be orthogonal. So that makes U3 E1 minus lambda 1 E1 E1 minus lambda 2 E2 E1. So that should be equal to 0. And nice stuff is that that's 1 because that's the norm of E1. And that's going to be 0 because E2 and E1 are orthogonal. That's how we build them. So we get lambda 1 is actually U3 E1. And similarly, you will get that E3 prime E2 should be equal to 0 because they have to be orthogonal, will be given by, so U3 E2 minus lambda 1 E1 E2 minus lambda 2 E2 E2. And that's 1, that's 0, and we get that lambda 2 is actually as we knew it would be because that corresponds to the components of U3 in the U1, E1, E2, E3 family, which is orthonormal. So it's given by the dot product, the scalar product of U3 with E2. Okay, and that's it. We've got everything we need. We knew U3, we have found lambda 1, we have found lambda 2. So now we have everything we need to make E3 prime. E3 prime is U3 minus it's the components of U3 along the previous directions. U3 minus scalar product with sorry, let me erase that, that's not nice. Scalar product with E2 E2, and we build E3 out of E3 prime as 1 over the norm of E3 prime times vector E3 prime. Okay, and now we've got this family E1, E2, E3, which is orthonormal. Okay, and so on. That's an induction process, right? When you have, assuming you have at rank K, so when I can write, so at rank K, assuming you have built this family B prime K, which will be E1, E2, EK, out of U1, UK, right? And you still have your basis B, that's the one. You want to add one more vector, so you want EK plus 1, right? So, and you're going to, so this part corresponds to that part, all right? They have the same span. Okay, they have the same span, and so you will get the same result, that E prime K plus 1 is going to be UK plus 1 minus, I'm going to subtract all the redundant information, being the UK plus 1 scalar product with EJ for J is equal to 1 to K. Okay, and then you can norm this vector and get the EK, sorry, I can't write, the EK plus 1 orthogonal